Hey, hope you're doing well. This is the second part of the ladder problem. And in this problem, I have the same ladder. The length of the ladder is 13 feet. The bottom of the ladder is moving at 2 feet per second away from the base of the wall. And instead of looking at the top and looking at the rate here, here's the new question. How fast is that angle changing when the bottom of the ladder is 5 feet from the base of the wall? So let's see how we can do this. I'm going to redraw the picture very quickly here. Wall, ground, ladder, angle, length of the ladder is never changing. Distance from the bottom of the ladder to the base of the wall is still x. Top of the ladder has a height of y from the ground. So what do we know about this problem? I hope you watch video 1 on this. We know that dx dt is equal to 2. We want to figure out d theta dt in this problem. When do we want to do this? When x is equal to 5. I am not going to plug this constant in. I'm not going to plug this constant in until later in the problem. So the first thing I need to do is come up with a model for this. So let's see. There's lots of ways to describe how theta, x, and y and 13 are related to each other. So there's sine, there's cosine, tangent, secant. Which one? So I'm going to write these all down. Give me a second. So there we go. Here they are. Remember, sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. So here are 6 trig functions. Now, any one of these is going to work, but some are a lot harder to use than the others. I know nothing about y or dy dt right here. I know that we did it in problem 1, but that's just an extra piece of information that I really don't need. So anything that has a y in it right now, I am just kind of get rid of it. And that gets rid of 4 out of the 6. The next thing I want to look at, where is the x in the problem? Is the x in the numerator or the denominator? Well, I'd rather have x in the numerator. So I'm going to get rid of that one. So this is going to be my model for this particular problem. So here's my model. Now I'm going to write the model like this instead. Cosine equals x. I just multiplied both sides by 13. Now what does this allow me to do? Well, I can easily take a derivative now with respect to time. 13 is going to come along for the ride. That's the constant multiplier rule. The derivative of cosine is negative sine. I'm going to leave the inside alone. And then chain rule gets me the d theta dt is equal to dx dt. I want to do this when x is equal to 5. So what can we do with this? When x is equal to 5, I still know that y is equal to 12. I mean, the Pythagorean theorem is still active here. I can still use this idea. And what does this allow me to do? Well, the sine of x, sine of theta, I'm going to put a little purple check mark next to it because right now, sine of theta, well, that's equal to y over 13, which when x is equal to 5, y is equal to 12. And that makes this 12 over 13. Theta equals, well, I don't really care. The question isn't about theta, it's about d theta dt. So using this little bit of information allows me to write the following. The dx dt was 2 from the very beginning of the problem. The 13s cancel. And now I have a very simple algebraic equation. Minus 1 over 6. 2 divided by 12. What are the units for this? Well, theta, well, they're going to be measured in radians. And time, well, everything was like 2 feet per second. So it's radians per second for this problem. So how fast is this angle changing when the bottom of the ladder is moving out at 2 feet per second? When the bottom of the ladder is 5 feet from the base? It's changing at negative 1/6 radians per second. Does that negative make sense? Well, if this ladder's slipping out, isn't the angle between the ladder and the ground going to get smaller? And that's what that says. And that's the end of part 2 of the ladder problem. I hope you found this video useful. If you have any questions, let me know. Have a great day. Bye.